Hello everyone. Today we're going to talk about the fluid compaction. The learning objectives of this class is to evaluate the state of fluid compaction with specification and to understand the mechanisms of the fluid compaction equipment acting on the soil layer. So we'll see what different kinds of the fluid compaction equipment are there and how they apply the external force to the soil layer. And the third objective is to identify the important parameters for the selection of field equipment and the design of the field compaction process. So first, let's talk about the field compaction specifications. So can we make field compaction prediction, so how well the field is being compacted, from the lab result? If so, what type of the specification can be made? So typically people use the two types of the specification. One is the end product specification, and we're going to talk about it soon. And the other one is the method specification. So today we'll go over what these specifications are. First, the end product specification. So in the end product specification, the owner or the project owner specify the final dry density or the dry unit weight of soil and water content. So field dry density and the field water content relative to the lab values are specified in this specification. Commonly, people use the 90% or the 95% of raw Dmax, so the maximum dry density obtained from the lab. So this gives you the concept of the relative compaction. So comparing to the laboratory maximum dry density value, if you compare that to the dry density in the field, you can quantify that the denseness of the soil in the field. So the example is, let's say that this is the curve that you get from the standard compaction curve from the laboratory, so that you know the dry density, the maximum dry density from the standard compaction test, and you specify the dry density range in the field to be achieved. So for example, if it's 90%, if this is specified, then you can draw the line, which is the 90% of the maximum dry density from the field, from the lab, and you have to achieve the contractor have to achieve the dry density at the field above this one. So this will be the minimum dry density then they are gonna achieve. And to achieve this dry density, they're gonna have to control the water content within this range. Otherwise, for the given compactive effort, they will not be able to achieve the dry density. And or sometimes they also specify the field water content. For example, field water content should be in plus minus 2% of the optimum water content obtained from the lab. So in this case, if you look at the curve here, if this is the optimum dry density, optimum water content, sorry, then plus 2% and minus 2%. So from here to here will be the range of this specification to satisfy the specification that's suggested by the owner. So we can introduce the concept of the relative compaction to inspect the field dry density. And the relative compaction is, we use the R, or you can use the RC to stand for the relative compaction. And this R is defined as the dry density of the field divided by the dry density, maximum dry density from the lab times 100%. So this is the definition is the relative compaction. For granular soil, the relative density is typically used, and the relative density is also defined as the void ratio in relative to the maximum and minimum void ratio. So dr stands for the relative density, and that's defined as E max minus E over E max minus E minimum. Here the E max is the maximum void ratio obtained from the lab, and there's a standard method suggested by the STM 4254, and the minimum void ratio in mean is the minimum void ratio obtained in the lab, and also there's a specification for that. So for the details you can refer to this document. And the E is the in situ or the field void ratio. So you can find the relation between the dr, the relative density, and the relative compaction R. So let's find that. So dr is defined as the function of the void ratio, and the void ratio is inversely proportional to the dry density. So E max is corresponding to 1 over D minimum, so minimum dry density, and the E is 1 over field dry density, and the E max is the 1 over minimum dry density, and the E mean, the minimum void ratio, will correspond to 1 over maximum dry density. So then if you manipulate and simplify this equation, you get this, and if we from the definition of the relative compaction, you know that this is 1 over R, right? And so it becomes this equation, and also this is the R, right? The field dry density over the maximum dry density, and we can also replace this minimum dry density over the maximum dry density as R naught. So replace this minimum dry density over the maximum dry density with the R naught. So then the equation becomes much simpler. So the dr is R minus R naught over 1 minus R naught times 1 over R. So the relative density can be correlated to the relative compaction with also R naught. So this R can be expressed as a function of the R naught and also the relative density using this equation. And here the R naught is the constant value, so it's fixed for a given soil because it's defined as the minimum dry density over the maximum dry density. Then empirical relation has been suggested by Lee and Singh in 1971, and the relation is R in percent is 80 plus 0.2 dr percent. And I recommend you to read this reference, the reading assignment. And the relative density also gives you the idea about how dense the soil is. So depending on the relative density, it can be categorized into 5 categories in terms of denseness. If the relative density is 0 to 15%, then it can be categorized as a very loose state, and 15 to 35 is a loose state, 35 to 65% medium dense, and above that is a dense state, and 85 to 100%, then it's called a very dense state. So let's solve the example here. For a granular soil, the relative compaction was estimated as 95%. So the R is 95%. And at that time, they estimate the relative density dr and they describe its denseness. So the R is 5 or 95. And you can use the empirical relation here suggested by Lee and Singh. So we can replace the R with the 95. So this will be 95%. So then DR is, if you calculate this, then DR becomes 75%. So according to this table, that's in this state, right? And it's between 65 to 85%. So it's a dense soil or dense state. So the field compaction specifications, there are two types. First is the end product specification, and this specification is used for most highways and the building foundation. So, and because the contractor is responsible for the result. So as long as the contractor is able to obtain the specified relative compaction, how he obtains and it does not matter, and nor does the equipment they use. So the owner will not care about what type of the equipment they use or how they obtain the result. So it cares only the result. So often specified as the percent of the maximum dry density of the standard product test. For example, 95% of the maximum dry density of the standard product test. You can say that. Or sometimes we'll provide the range of the water content. So control the water content to be plus or minus 2% of the optimum. And contractor responsible for achieving the dry density, ROD, and owner inspects for density only. And contractor will use a slightly higher compactive effort to achieve the requirement to satisfy the specification. And the other method is called the method specification. And this type, the type of the roller or the type of the equipment or the weight of the equipment, the number of passes, and as well as the lift thickness are specified. So in this case, all kinds of all details of the method that the contractor have to use is specified. The maximum allowable size of the material may also be specified. So let's say that the owner can say that you have to use this size of the gravel, or you have to use the soil have 10% of the silt only. Those kind of specification can be made. And so because the owner specified all the method and the details, what materials they have to use, contractor has to use, so the result is responsible by the owners. So when you check the ROD, the dry density, if not happy, that owner will have to pay contractor more to do more compaction, or they can change the design too. It is typically used for large compaction project. So an example of the method specification is given in this table. So the type of construction is the backfill, MSC backfill, and you have to tow the roller 6 passes, and the equipment has to be like 10 ton. And for the segment 2, for the section 2, so 7 passes, and the lift is 30 centimeter, and the 5-ton vibrating roller, and segment 3, so it's 3 passes and 30 centimeter lift. So lift is the thickness of the layer, and 1,000-pound plate temper, so things like that. So you can see that depending on the segment, so it means that like this 1 kilometer is one segment, and after that another 1 kilometer, the segment 2, like that. So for each segment, all the methods for the compaction is given. Okay, so continuing from the field specification, let's talk about the field compaction process. So these slides are based on the chapter 5 in the textbook by Holtz and Kovach, and section 2.2.2 in the textbook by Hausman. So for the details, I recommend you to read these two materials. So let's move on. So in the field compaction, let's define some terminology here. So borrow pit is the place that you borrow the material, and then you dump the soil and make it spread to be filled. So excavator remove the soil from the borrow pit and dump the soil at a given location and spread, and then the compactor will come and they will compact the soil to densify the soil. So borrow pit is, the definition of the borrow pit is an area where the material has been dug for another location. And in the field compaction, usually compaction done in layers, and it's called the lift. So the layer thickness is also referred to as the lift thickness. So spread the material in layers, normally like 15 to 45 centimeters. It's called the lift. And then you tow the rollers, so compact the soil. In this case, also number of passes will be specified, and the weight of roller and the speed of roller will be specified, and control the dry density and the water content for each layer, so you can achieve the targeting dry density. So you can see that the one layer is one lift, and it has a certain thickness, and the weight of roller and the number of passes are specified so that they can control the compactive effort. So field compaction equipment. First one is a smooth wheel roller. It has 100% coverage under the wheel and contact pressure up to 400 kilopascal, and it can be used all type of soil except for rocky soil. And compactive effort is a static weight. Because it's flat and it's smooth. The common use for large smooth wheel roller is for proof rolling subgrade and compacting asphalt pavement. Then the second is the pneumatic roller, rubber tire. So you can see that there's a rubber tire and 80% coverage under the wheel. So because it's 80% because you have a gap in between. And the contact pressure is 700 kilopascal and can be used for both granular and the fine grain soil. And compactive effort is a steady weight and also the kneading. And ship's foot roller, you can see that at the drum you have a protrusion like this. So this is the most common type for the fine grain soil because it has a kneading effect. And has a many round or rectangular shaped protrusions or the feet attached to the steel drum. 80% to 12% coverage, and contact pressure is from 1400 to 700 kilopascal. So for the kneading effect, it has a very high contact pressure. Also, it has a small area to contact. So for a given weight, the weight is concentrated in a certain area so that you have a high contact pressure. It's best suited for the clay soil. The compactive effort type is a steady weight and the kneading. And similar to the ship's foot roller, you can see that there's a different type, also the tamping foot roller. It's about 40% coverage and also has a high contact pressure, and you see that it has a tamping foot, like a small protrusion, and it's best for the compacting fine grain soil also. Steady weight and the kneading effect is the type of the compactive effort. So the tamping foot roller compacts from the base of the layer to the top layer, and it walks out when lift is compacted and used with the fine grain soil, and foot is normally round or rectangular. So you can see that this one is kind of rectangular, and this one too, also the rectangular. Vibratory soil compactor. So here you have a smooth wheel roller, but they added the vibration, vertical vibrator attached to the smooth wheel roller. So best explanation of the wide roller vibration cause densification of the granular soil is that this vibration is really effective for compacting the granular soil because the particle rearranging occurs due to cyclic. deformation of the soil produced by the oscillations of the roller. So as you vibrate the soil, it reduces the frictions so that the particle can move it very easily, so that they can rearrange the positions to be more denser state. And compactive effort type is steady rate plus the vibration. So this is suitable for granular soil. And dynamic compaction, so it doesn't show the movie here, but so you have a heavy weight and they just dropped on the ground surface. So by dropping the heavy weight, that load, it applies the impact force to the soil, and it's called a dynamic compaction. You can achieve the densification to the depth of about 10 meters, so it's called a deep compaction method. But the other rollers are shallow compaction, shallow surface compaction method. We're going to talk about the deep compaction, deep surface compaction later, maybe the next week. So compaction method is static compaction and kneading compaction and dynamic compaction. And in the laboratory, as we drop the hammer in the standard Proctor test and the modified Proctor test, we use the impact force. And the kneading is very good for the fine grain soil, and the vibration is good for coarse grain soil. And steady is not very efficient, but the people use it for asphalt and the subgrade soil. So the equipment summary. So you can see that from here to here you have a larger grain size. So rock has the largest grain size, and the clay has the smallest grain size. So as you go to the right side, the particle size increases. And the sand and the rocky and gravel, you can see the vibration is very effective. And smooth steel drum and pneumatic drum, and as you go towards the clay soil, you can see that the kneading effect is getting added more. And the clay chips foot roller is the best applications.